This conference will now be recorded.
Hello, everybody. Jordan Girth here with the National Weather Service Office of Observations. Thank you so much for joining us for the Satellite Book Club Seminar Series. This is session number 170. The title of today's presentation is the GOES-R Geostationary Lightning Mapper in Research to Operations Paradigm. I'm pleased to have Kevin Thiel, the GOES-R Satellite Liaison to the Storm Prediction Center and NOAA's Hazardous Weather Testbed with us today. Following Kevin's presentation, we will have a discussion facilitated by Brian Curran, the Science and Operations Officer at the Forecast Office in Midland, Texas. As you just heard, this session is being recorded, and as usual, there will be Q&A after the presentation. If you have not signed in with your full name, please note your name when asking a question in the chat, and that will allow us to follow up. Otherwise, we will address the questions in the chat in the order they are asked. If you are interested in being a future presenter as part of our Satellite Book Club, please contact members of our TowerS team, Gashad Bowman and Emily Maddox. The training team can also help create training materials or point you to materials that you may be unaware of or are unavailable. Contact Ross Van Til with the Office of the Chief Learning Officer for more information. I'd like to thank our TowerS team, particularly Gashad Bowman and Emily Maddox, the Office of the Chief Learning Officer, the GOES-R and JPSS programs, our presenter, facilitator, and all of you for being with us today. Without further ado, I'd like to formally introduce Kevin. Kevin Thiel is a research meteorologist for the University of Oklahoma Cooperative Institute, or CIWRO, serving as the GOES-R Satellite Liaison for the Storm Prediction Center and NOAA's Hazardous Weather Testbed. He leads the Satellite Proving Ground Hazardous Weather Testbed each spring and works with the Storm Prediction Center forecasters to integrate satellite data into operations. Kevin is a meteorology candidate working on his PhD for the University of Oklahoma School of Meteorology, studying operational applications for the GOES-R Geostationary Lightning Mapper. So this fits very well. Kevin, welcome back to the Satellite Book Club.
Thank you, Jordan. Yeah, I'm really excited to be back here at the Satellite Book Club. And this is going to be a talk that's going to expand a little bit upon what I presented at the National Weather Association's annual meeting. There was someone that had mentioned that they had wished that talk was longer and had more in it. So if that person today is your lucky day, this is an expanded version of that talk. And we integrate a lot of information here talking about the Geostationary Lightning Mapper in the kind of research to operations paradigm, what gets learned from the research side, what gets learned from operations, and kind of that cycle that goes back and forth today. So we'll be covering a lot of different topics throughout this talk. So for those who aren't as familiar with the Geostationary Lightning Mapper, that's okay. I'm going to give a one-slide crash course on the GLM just to get everybody up to speed. This also will help as a refresher and help set the stage for some things that I talk about later. The Geostationary Lightning Mapper, at its core, you could think of it as a high-speed camera that's capturing rapid changes in pixel brightness created by lightning flashes. So as the lightning initiates, and then you have the channels that then are emitting light, that light propagates through the cloud, escapes from the top or sides of the cloud, and is then picked up in rapid changes in the brightness by the Geostationary Lightning Mapper. That wavelength is just beyond the visible spectrum, right in the near infrared. You'll oftentimes hear it called an optical detector, though. It runs at about 500 frames per second and covers much of the eastern or much of the western hemisphere from the GOES east and west perspective, as you can see in the figure here in the bottom left. Now, those individual pixels that are picked up by the GLM, those are what are classified as events. So every 2 milliseconds, you'll have those individual pixels, and those adjoining pixels are then put together into groups. Those groups are then spatially and temporally clustered into a flash. So this example from Goodman et al. 2013, we see the adjoining pixels or those events that are then put together into groups. And then you can imagine that these are then spatially and temporally clustered into a single flash in those kinds of cases. And that's how we're able to then get from the pixels to the flashes that then the GLM is able to pick up. Now, we could just give forecasters events and groups and flashes and say, congratulations, you now have all of the GLM data at your fingertips. But when looking at this figure here from Bruning et al. 2019, there's a lot of information that gets lost actually when giving all the information. We don't really understand flash characteristics, but looking at just data as these individual points in these cases, what's really going on up in these areas? Do we see more flashes up here? Do we not? Where are these flashes going? Where are they propagating? We just don't know that information. And so, as described in Bruning et al. 2019, gridded imagery were then developed for the GLM to then take that spatial context from the GLM and union that with the flash level characteristics, whether that's the rate of flashes, the area, or the brightness of the flashes observed from the optical detector. And so we're then able to translate that into usable information for NWS forecasters. In order to bridge the gap between the launch of the GOES-R GLM back in 2016 and the creation of the implementation of the operational imagery that happened earlier this year, one of the many efforts that happened as part of that was placing the geostationary lightning mapper imagery into NOAA's Hazardous weather testbed, providing a great source of feedback and a way in which we can understand how we can apply the geostationary lightning mapper. And so today I'll be talking a lot about the applications from the GLM and what was then uncovered along the way that we then understood as well to help drive even new science out of the HWT. Now, NOAA's Hazardous weather testbed, giving kind of a summary of that, this is a really great space that's created here in Norman, Oklahoma. We also are able to run this in person and virtually as of this last year. But we're able to combine the developers and the research scientists and even just subject matter experts that are able to then observe forecasters in this kind of space. And so we're able to create a setup where we can provide applications, limitations, understand even things down to display techniques, and also motivate ideas for future research. And that's something that I then sit there and I organize every year and find ways that we can better provide useful evaluations and feedback that then benefit not just those that are developing products, but also the operational community in creating this transition from the research to the operations. Within the Satellite Proving Ground, we use live data with NWS forecasters, and so they're getting a simulated kind of real-time warning environment. So even on those days when we have more marginal cases, those are still insightful because nobody really knows what's going to happen until it happens. And so this creates this sense of operational relevance, whether that's things like issuing warnings. And we also create what we call simulated DSS events as well to help facilitate the idea and focus on the Weather Service's expanding mission in decision support service. And so all of this is then wrapped up within the testbed, and we're then able to get a lot of really great feedback and results. And we'll be focusing on that throughout the rest of the presentation. There are three main products we're going to focus on today from the GLM. The first one is flash extent density, or FED. This is the number of flashes that propagate through a pixel over a given time period. So you can imagine as you have higher FED values, more flashes are propagating through that area. It's most likely to correlate with or correspond with your thunderstorm cores. Minimum flash area is the next product we'll introduce. This is the smallest available flash area from all the flashes that propagate through that pixel over a given time period. This one may not make as much sense up front, but it is quite important, as I'll explain a little bit later. But what you can think about is, out of all the flashes that propagate through these pixels, as we can look at the FED, which flash, or what was the smallest area that was available from those flashes? Think about with the GLM, knowing that it has at best an 8-kilometer resolution. We're talking about flash areas that are roughly between about 60 to 70 square kilometers there at its smallest level there, especially as you get in across the CONUS, they might be up to 70 or 80 or so. Total optical energy is the last one, and this one is, you can think of it as the most native product for the GLM. This is the accumulated optical energy from all pixels the GLM observes over a given time period. Oftentimes, these given time periods are going to be 5 minutes updating every minute. That's what forecasters tend to like the most within the testbed, and they find the most useful for looking at trends. But these data are also available as 1-minute imagery as well. Now I'm going to kind of skip to the end and then kind of come back just to help kind of motivate some what the general themes that we're going to cover throughout the rest of the talk. But we're talking about things like how confident and how useful the GLM data are, and we can ask forecasters this using daily surveys. We can get feedback in terms of blog posts and a lot of other, and even just having discussions with forecasters directly. In the 2022 experiment, we asked forecasters how confident and how useful they felt each of the GLM products were each day. And what we can notice here on the left plot, when looking at the red, FED, the flash density, peaks at very high in terms of its confidence. Minimum flash area does as well. However, total optical energy has peaks at around the medium confidence range within the area, and is more dispersive in terms of the types of responses that we get from the forecasters. When asking how useful each of the GLM products were, we again see that flash extent density, as was noted, as extremely useful, the highest level available. We see very useful here with minimum flash area. However, total optical energy is further down here, as we note with as most often responded as somewhat useful. And so we see these kind of differences in confidence and utility, and this leads to the why. And my hope is that I can then answer the why with the applications that forecasters have given and also their feedback along the way. So the first main applications we're going to talk about is probably the biggest one, and this is the inverse relationship between flash rate and area. So on the right-hand side here, a figure from Bruning and McGorman 2013, looking at panel B, we can see around an updraft where you have lots of mixing and lots of turbulence around the updraft, you're then going to organize your charge regions into smaller and smaller areas. So you can get more flashes to initiate in these smaller oppositely charged regions, but they're going to have a smaller areal extent. So lots of flashes, but they're going to be smaller. Vice versa is then also true in areas of more stratified precipitation, especially these stratified layers. We have fewer flashes, but they're going to have a larger area because the charge regions are physically larger. Within our GLM gridded variables, that's what we observe, as we see increasing FED commonly corresponds with decreasing minimum flash area. This animation here in the lower left-hand panel shows that quite well, as we have an increasing FED maxima associated with the supercell in the southeast, and we also then see the smallest available minimum flash area values here, these bright yellows, and those correspond with the issuance of a tornado warning within the simulated HWT that actually ended up verifying. And so forecasters can use these signals in tandem to understand when a storm is intensifying, along with also decreasing in intensity as well, and to identify those thunderstorm cores and being able to track them spatially in time, along with pairing those with those ground networks as well to look at the total flash rates. This is not just something we can use in just limited case studies. This is something that applies in bulk as well. These figures are actually from some master's research that I did a few years ago, and we looked at a bulk study over the GOES East CONUS domain, 7 weeks of data in April and May of 2019. We ended up with about 3.6 million data points that we ended up sampling. So a lot of data went into these plots. We then binned that data by temperature from the ABI, the clean IR brightness temperature, that channel 13, and then also by the ABI cloud top height product. And so you can imagine the upper left-hand corner here, this is going to be your coldest and highest cloud tops associated with the most intense convection, while further down to the bottom to the right, that's where you're going to have your more weak or modest convection, or things that are on the kind of the edges of your storms. And what we noted is that as you translate into that intense convective area, we see increasing median flash extent density values, and those values then increase from FED. When looking over at the minimum flash area, we see the inverse relationship is then present there, where we see the smallest available flash areas at the highest and coldest cloud tops from the ABI. And so we can then correspond those two and then provide a more definitive proof of that inverse relationship exists in general between the flash extent density and minimum flash area. Now, in terms of even just warnings, going just one step beyond that, GLM can also readily be applied for decision support services, or DSS. When we provided the simulated events for the forecasters to then provide messaging for, one of them is up here in the top left-hand corner, where a forecaster exploited the footprint of the flashes from the GLM and showed that as a storm was approaching a baseball tournament in Florida, that there was flashes that were propagating out ahead of the thunderstorm core. This is in an area that had pretty low vertical shear, or very low vertical wind or horizontal wind shear. And so you had then the anvil overspreading the event already and creating a lightning threat before the storm even got there. And the forecaster could then message that to the event organizers or even the general public. Forecasters also were able to show in the bottom right-hand corner here a really fun example from the 2021 testbed of a decaying MCS, being able to identify those large flashes and where those are propagating. And so we can observe those in the red encircled regions here. As the animation plays out again, we'll be able to see those purple flashes here in the minimum flash area product, highlighting that we have flashes that are propagating 2 to 3 counties to the west of that decaying line. So even after that storm was passed, there's still convection there's still lightning that's being produced in that area and producing that threat. You can then even pair that with the ground networks as well and identify where those are coming to ground. Now, I mentioned merging the cases with the ground networks, and this is similar here, as we can see from that same case from before, just taking a simple screenshot from that time. What's plotted here are the ground networks this is from the Earth network's total lightning network. And so we have the intercloud flashes circled here in white to help make those more visible. And then we have the red circles here are the cloud to ground flashes. And so when using these two networks together, you can identify where those flashes are coming to ground. If you didn't have the GLM, a forecaster might be led to believe there may be location errors in these data, and that's why you're observing these kind of random flashes that are so far away from that main convective line when things really don't look all that impressive from radar. So this can provide a really nice way to actually trust your data. And by using both, this provides a more complete view of the lightning picture that you can then provide, whether that's in a warning perspective or even with the DSS and lightning safety as shown here. I do want to kind of take a brief aside and also talk about large GLM flashes. Those can be covered as well and help be and based upon kind of that idea, we then wanted to characterize those environments. And so recently in a more recently published study, we combined not just the GOES-East GLM and ABI, we also merged it with radar from the MRMS system. Using that same data set, we ended up yielding about 2.8 million points and binned that rather than now by temperature, here on the x-axis, that brightness temperature from the clean IR band, we can now bin that by the negative 10 degrees Celsius isothermal reflectivity from MRMS. And we can now understand the kind of glaciation rates from cloud top, along with the amount of precipitation that's being lofted into the mixed phase region as well. And when binning and when looking at the minimum flash area in this temperature and reflectivity perspective, we see a peak in our minimum flash areas within this zone here, right about 210 to 230 Kelvin and then 20 to 30 dBz. These line up pretty well with a few past studies about where flashes propagate in terms of regions of reflectivity. But even when using a simple, just at one isothermal level, you can provide a lot of great information there. And so this is a case from a GLM flash, or some large flashes that were propagating north of this kind of also kind of decaying MCS region into southern and central Oklahoma. And when looking at the clean IR brightness temperatures within this region are right around 210 to 220 Kelvin. And if we look at that same region with that negative 10 degrees Celsius reflectivity, it's right at about 20 to 30 dBz. So even in the real world, these tend to line up really well and can give additional insight now on what areas that a forecaster can watch out for in terms of a lightning threat, and where those flashes are then propagating. Shifting gears now to a slightly different topic, looking at the GOES-East versus the GOES-West GLM and understanding which one to use and when. We posed this question to forecasters, and that's something that we wanted to get in. We were able to get some really nice answers from. When looking at some of the previous research that had gone into this kind of question, we can look at Bateman et al. 2021, where they looked at the GOES-East and West GLM detection efficiency using a simulated network. And what they generally observed is that as you get near the edges of the field of view, so across most of the western US, your detection efficiency does decrease from the GOES-East GLM. And then in a sense, vice versa, as you go across most of the kind of the northern plains into the Midwest and also into the Southeast region, you see decreasing detection efficiencies as well from the GOES-West GLM on average. When combining those in the area of sensor overlap, as done by Rodlowski and Verse 2021, right at around 103 degrees west, that was defined as a rough kind of line between where, on the right here in the blue, these are the regions where the GOES-East GLM is observing more flashes than GOES-West, the percent difference in the flashes here. And then on the left hand side here in the reds, that's where the GOES-West GLM typically observed more flashes than the GOES-East GLM in another kind of bulk study in that kind of sense. So on average, this presents kind of some general insight we can use to then apply to that problem. Within the testbed, we created procedures for forecasters to look at the GOES-East and the GOES-West GLMs and being able to compare them in the regions of overlap. And we then advocated for forecasters to view these data more often, right at about that central mark. And we wanted to understand what forecasters picked up on, what they found was useful along the way. We didn't have as many samples as we would have liked. We did get some really nice cases out of it. One case here, as we showed here on the right, is where the forecaster observed different FED values from the same storm here about western Nebraska and eastern Wyoming, right along the border there near Scottsbluff. And so from the GOES-East GLM, they observed fewer flashes, but from the GOES-West GLM observed more. And the forecaster noted that in this shared environment, that you would have, that from the GOES-West GLM or GOES-17, you would have more light emanating from the side of the updraft as well, that then is creating a stronger optical signal that then the GLM could pick up on with those with those detections. And so this provided then that kind of environment. Now, how we then translate this to forecasters and how we can provide this in a larger sense can be difficult. Though we have a really nice outlet and a really nice support here actually in the Weather Center, working with the Warning Decision Training Division. Katie Christian last year took these testbed results and took the initiative to update the Walk Severe GLM course, which we're very grateful for her for doing that. And WDTD continues to update the modules as we continue to have results from the testbed, and took that example and was able to then put that into a learning module for forecasters to then use when they're taking these trainings. And understanding when to use each GLM, depending on where you are in the US, depending on the time, depending on which, just the environment that you're actually looking at. So we're very grateful for that. As we also get to the other edge of the field of view, while I also mentioned that, of course, with the flash density, you might have lower detection efficiencies. And in those cases, it might be more difficult to identify updraft cores because of that lower detection efficiency. However, with minimum flash area, because you're looking at the characteristic of a flash, it only takes one small flash to then identify an updraft core in these areas. So on the left-hand side here, this is an example from up around the Dakotas. This day, the forecaster was looking at the GOES-East and West GLMs and noted that while the FED values were quite small, and they really didn't see a signal of the updraft cores within that product, they could readily pick that up with the minimum flash area product near the edges, because that's one that's limited by the characteristics of the flashes themselves and not as much by the detection efficiency. When looking at it from the GOES-West perspective, in this area, there actually are a few cases where you see, again, more updraft cores that could be identified. In those cases, if you go back and forth, This is a case where maybe both GLMs could be useful to use, but making sure that you always keep parallax in mind as you're going to have a shift in these data as you go from one to the other. A few other miscellaneous questions that we brought up regarded the display and the visualization of these data, especially in terms of flash extent density, which forecasters really strongly gravitated towards within the test bed. And we asked forecasters, is the default maximum on the color bar sufficient for what you need each day? And so the current default within AWIPS is 260 flashes. However, we noticed in a number of cases, forecasters were using much lower maximum values on their color bar range to help bring out more gradients at lower values. And so we wanted to understand if, well, while the 260 flash maximum maybe is really good for intense convection like supercells, it's probably not, it may not be as useful for marginal and cool season events. So in the bottom right-hand corner is an example of a procedure we made for the forecasters to look at, where they looked at the maximum FED value at 260, that default in the top left panel. On the top right panel, this is 130, so we halved it. And then in the bottom left-hand corner, this is 65. So now it's a quarter of the maximum. And we asked forecasters to compare that with radar imagery to understand how these trends that we observe in the in FED, if those features have been brought out visually to the forecaster in comparison to what they would observe from radar or from other satellite imagery. When asking forecasters each day how they felt each one was useful, forecasters tended to find that setting it at a much lower value, around 65, was most preferred to them. 130 also was quite useful, and some forecasters even went as far as going even less than 65, sometimes even down to 20 or 30 flashes, especially when looking at initiating convection or in areas where your flash rates they knew were going to be pretty marginal based upon their environment. And so that can help to identify the strongest storm, but then also other intense storms in the area by lowering that value. So in translating this as well to training, we can go back to the Walks of Your GLM course, and they also provided additional clarification on that and translated that information that you can oftentimes adjust that default color bar maximum value down to 130 flashes per 5 minutes if you need to. But sometimes maybe it's better to make procedures that are tailored to more warm or cool season events or more marginal or intense events, depending on where you are in the CONUS. And so that's a really great translation of taking what we have observed, creating a way in order to test that, and then providing those products here. Now, the last section I'm going to talk about here is total optical energy, which you might have noticed I haven't really mentioned a lot, and that's mostly because, in short, it can be a bit more complicated with how to actually apply that. But the big takeaway is that the total optical energy can provide context as what the GLM observes. To give a physical basis for this, looking in the left-hand corner here, this is a figure from Brunner and Bitzer 2020, where they simulated a supercell in WRF and then initiated a lightning flash, and using a Monte Carlo simulation in different microphysical environments, then we're able to capture the amount of light that escaped from the cloud top here in the left panel, and then from the sides and the bottom of the cloud here in the right panel. And while we notice here different environments can yield different amounts of light escaping from the cloud tops and from the sides especially, that the initiation height and the emission source height from the flash really is the big driver of how much light escapes from each section. So even as you have lower flashes in the cloud at around that kind of common area between about 6 and 8 kilometers where you would typically see most flashes, that quite a bit of light escapes from the side. And so what this really comes down to is the path that the light then takes from the lightning flash itself, from those channels through the cloud and to the sensor. That matters. In the right-hand corner here, this is a figure from a paper we recently put out comparing the GOES East and West GLMs of a supercell in Kansas. So while GOES East here is a little bit closer, it's quite comparable in terms of the viewing angles, about 50 and 60 degrees respectively from zenith. And so what we notice is that our FED values here are quite comparable here. From the GOES-East GLM here on the left, that's a little bit higher. However, we see a really large disparity in the total optical energy from the GOES-West GLM as being much higher than what's observed from the GOES-East GLM. And so in these kinds of cases where you have more strongly sheared convection, as you mentioned earlier, you're then getting a stronger optical signal and picking up on flashes in these areas and able to then provide a different view of your lightning as compared to what you observe from the GOES-East GLM. And so really, just to help kind of boil it all down to something more simple, total optical energy provides that context of what the GLM is observing and can be used in a sense as kind of a data quality product to use on that end. And you can use it to identify thunderstorm cores still in some cases, but that relationship isn't always a one-to-one. So to wrap things up, what we've learned in the test bed so far and putting everything kind of together into one single slide with flash extent density, this is an excellent base level product. You can get the aerial extent of the flashes in a general sense. You also can know and being able to identify increasing flash rates locally within thunderstorm cores. Knowing when to use each GLM or both can be quite useful in operations and how to kind of mix the two together in procedures. That can be difficult with limited screen space at times in AWIPS and also bandwidth, but something that you can also consider there as well when making procedures ahead of time. Oftentimes you can reduce the maximum default color value maximum in AWIPS to 130 or 65. Those are general values that forecasters picked up on and liked, but that can be dependent on your environment and what you then need to use as a forecaster. Minimum flash area is also a pretty handy tool to use as well, whether that's standalone or in tandem with flash extent density. Being able to identify those increasing local flash rates from FED and decreasing flash areas from MFA can then be useful to identify strengthening updrafts. Also, the larger flashes and knowing where those are and where they're propagating can be useful in terms of DSS. And then as you get near the edge of the field of view, especially you can use minimum flash area to help identify those updraft cores as well. Total optical energy, as I mentioned, while it can be a little bit more complicated and has a few different kind of features, can be more useful as a data quality kind of tool and being able to understand the context of what the path is that the light is taking then to each sensor and the context around each of your minimum flash area and flash extent density values. And then the last thing I'll mention here is that the GLM is a product that is not best when used alone. It's best when used in tandem with other products, whether that's with radar or satellite imagery from ABI, and especially when used in conjunction with the ground networks that are available. So whether that's Earth networks or NLDN, if you have a local LMA feed that's coming into your office, that's great. You can use that as well. But providing this more complete perspective of lightning activity is a big kind of key in that as well. So wrapping up here, I cited a bit of literature here within this presentation. So here's a quick kind of overview of the references to have those on file. And I really appreciate the time to be able to talk about everything within the test bed. This doesn't happen without a lot of people involved beyond just myself. I came in about the halfway point of the evaluations in 2021. But there are a lot of really great people that have done this and help support this work within CIWRO, within the GOES-R and JPSS programs. Also shout outs to Kristen Calhoun and Jonathan Madden and Justin Monroe for all their great work with organizing the testbed over the years and helping facilitate that even from before my time and as I came into this position. All the forecasters and the researchers and subject matter experts that have came and viewed the testbed as well. Those are all big pieces to being able to translate the research that's done into operations. And I'm very grateful for that and being able to share that with you all today. So that's everything I have for today. So I'll throw it back over to the organizers and I'd be happy to take questions if we've got time.
Thanks, Kevin, for your most excellent presentation. I can see that there's a lot of potential in using GLM data to illuminate the convective weather forecasting and diagnosis techniques. I'll stop with the lightning puns now. For folks on the call, please stay on for the discussion. If you're from a field forecast office or a regional headquarters office, please specify your full name in the chat when asking a question. Also, Emily here will be posting into the chat room a feedback survey for the Satellite Book Club. Please take a moment to fill out that information, and it will help us help you. So a week from today, on Thursday, December 7th at 12 p.m. Eastern Time, Dan Bilkos from CIWRO will discuss data fusion in short-term forecasts and warnings, which looks like that'll be an interesting talk. Also, contact the TowerS team, Kashad Bowman and Emily Maddox, for questions about the Satellite Book Club or for configuration of satellite book clubs. And so with that, I think we've got time for some questions. We'll start off with Scott Lindstrom. He asks, are there any GOES-17 versus GOES-18 differences in GLM detection?
Yeah, that's a great question, Scott. And I don't have an exact answer that I could give to that in terms of what I've observed. I do know that when on the launch of GOES-18 and the GLM, that there were some things that were done to help mitigate solar intrusions, so light coming in from the sun, so lower reflections. And so in general, from what I've been told and what I've observed, that the GOES-18 GLM should have a slightly higher detection efficiency in comparison to the GOES-17 GLM. In a broad sense, I haven't seen how that really pairs out yet in terms of individual storm performance and such. So hopefully that answers your question there. But yeah, that is a really great question to consider as we kind of compare these data and are rolling between different satellites.
Okay, Jordan Girth has a question, and this pertains to the northern latitude WFOs. Montana, Wyoming, and the western Dakotas have poor detection efficiency from both GOES East and West. What advice do you have for WFOs serving those areas?
Yeah, so I think one of the things that I mentioned is being able to leverage as well your ground networks in conjunction with with the GLM. That'd be the first thing I would consider. So making sure you always have those together. But then also, as I had mentioned, especially pairing flash extent density with minimum flash area. So that way you aren't just looking at the total number of flashes, which are strongly influenced, of course, by detection efficiency. But if you're looking at the flash characteristics, then you're able to separate a little bit more out from just the detection efficiency differences. And you can then get at those characteristics, especially in terms of updraft cores and looking for those overall convective trends. One of the other things that I would kind of market as part of the GLM in those areas where you maybe have more sparse radar coverage is that because you're able to get these data in every 1 minute, you can then provide more rapid updates in these areas in comparison to what you could get from radar from a full volume scan as well. So being able to leverage comparing the GLM gridded products with the ground networks, using minimum flash area as well to help in those areas of lower detection efficiency. Those are the kinds of things that I would strongly advocate for forecast or WFOs in those areas to use.
Cool. Lee Byerly has a question. For NWS AWIPS users, do you know if there are preferences regarding the 1 minute with 1 minute update or 5 minute accumulation with 1 minute update gridded products or other preferred accumulations? And I will say that I prefer the 5 minute accumulation with 1 minute update, as that tends to pair with the volume scans from the 88D. Do you have any know of any preferences there?
Yeah, Brian, I mean, the preference that you expressed was pretty much the consensus that we found within the test bed. Some forecasters did use the 1 minute summation with the 1 minute update, but most often forecasters gravitated towards and liked using the 5 minute accumulation with the 1 minute 1 minute updates for the exact reason that you said, that the values that you're able to observe in each are less sporadic and jumpy, and you can then more readily identify those trends that are happening on the order of 2, 3, 4 minutes more readily in those cases. I know there are other times when we think about, I know if you've ever seen the GLM stoplight product that's being worked on down in Huntsville and NASA Sport and UAH, that they're using a 30-minute accumulation of the gridded products as well in those kind of cases. And so working with those longer ones is not something we've done a whole lot of beyond, I believe, the 5 minutes span. I have to go back and look at the 2018 and 2019 experiments. Those would probably be where we would find that. But in general, yeah, I mean, what you said, Brian, is very much true. It's the 5 minute accumulation with the 1 minute update is the most preferred by the forecasters.
Okay, I think we've got time for one more question, and I apologize, Ian, if I butcher your last name. Ian Arvrich says that you mentioned a difference in detection efficiency between GOES East and GOES West due to the observing geometry. Is there a combined GLM gridded product?
That's also an excellent question, and my personal response is I wish there was. But right now there is not. There's some difficulties in being able to do that right now, along with considering things like parallax. Also understanding kind of the different geometries of the flashes. Being able to combine those is something that, especially for national centers, I think could be really useful. But it's not something that we currently have right now. But that's something that I would definitely encourage as kind of a future research as we continue to leverage the GLM throughout the rest of the 2020s into the early 2030s. So right now we don't have one. I would like to have one though in the future.
Right, because my CWA would be a perfect test bed for that, being straddled along that longitude. In the interest of time, I think we'll wrap the questions up. I guess right now we'll kick it back over to Jordan and for closing remarks.
Thank you so much, Brian, and thanks for that presentation, Kevin. Great information on the GLM, and look forward to working with you as we head toward the spring months to make sure our field offices are able to leverage that data to the fullest extent. And I know you've put a lot of time and effort, and good luck as you wrap up your PhD. As has already been mentioned, next week the Satellite Book Club continues with Dan Bykos from CIWRO. So please join us again at our normal time of 12 noon Eastern time. In the meantime, if you could do me a favor and talk to your SU or ITO and ask them, do we have the latest TowerS RPM installed? If you don't know the answer to that. And if they say, I don't know, or no, have them contact Ashad Bowman or Emily Maddox and get your office on the list to get the latest TowerS RPM, which has all the latest configurations for satellite products. Also, if you want to present as part of the Satellite Book Club, Kashad and Emily can help with that as well. So we'll wrap it up there for today. I really appreciate everybody joining us. Please, I hope you'll be with us again next week for our Satellite Book Club seminar. But that is it for today. So take care, everybody. Thanks so much, and so long.